This video is about analyzing electric circuits using superposition. The superposition principle says that the effects of all the sources with corresponding stimuli on a circuit of linear elements is equal to the algebraic sum of each individual effect. Wow. That's a mouthful. They say a picture is worth 1,000 words. Well, here's a picture to illustrate that principle. A circuit with 2 batteries will have the same current as the circuit with only one of the batteries, plus the circuit with the other battery. That means if we have a circuit with 2 batteries, we can solve the voltages and currents with only one of the batteries, then solve the voltages and currents with the other battery, and then add them together for the real voltages and currents in the original circuit. Here's a circuit with one 10-volt voltage source, one 2-amp current source, and 3 resistors. Let's use superposition to solve the voltage across and the current through all 3 resistors. The first step is to redraw the circuit with only one of its sources. We replace all of the other sources with their ideal internal resistance. Ideal voltage sources have no resistance, so they're replaced with wires. Ideal current sources have infinite resistance, so they're left open. The battery in this circuit is a voltage source, so I'll draw a wire where it used to be. Now, we're going to solve for the currents and voltages and map all of them back to the original circuit. The 6 ohm resistor and the 4 ohm resistor are in parallel. So we can find that parallel resistance by taking 1 over 6 plus 1 over 4, inverting it again, and we get 2.4 ohms. Now the 2 amps that flows out of this current source flows through that equivalent resistance, through that 12 ohm resistor, and back to the current source. Since it flows from the bottom to the top, the voltage across that resistor is in this direction. And the voltage is going to be 2.4 ohms times 2 amps. So we have 4.8 volts. That means there's 4.8 volts across this resistor, and there's 4.8 volts across this resistor. If we know the voltage and we know the resistance, we can find that current. And that current is going to be 4.8 divided by 6, or 0.8 amps. The current through this resistor is going to be 4.8 volts divided by 4 ohms, or 1.2 amps. 1.2 amps flows up this way. 0.8 amps flow this way. That adds up to 2 amps flowing through that 12 ohm resistor on its way back to the current source. Let's map those values back to the original circuit. We have 2 amps here, we have 1.2 2 amps here. And we have 0.8 amps here. Those are all the currents that are flowing in that circuit because of the 2 amp current source. Now we redraw the circuit with its other source. This time, we're going to replace the current source with its internal resistance. And since current sources have infinite internal resistance, ideally, we're going to leave that branch open. That means we're going to have current flowing out of the battery, around the circuit like that, and back to the battery. The current through this 12 ohm resistor here will be 0 because it has no place to go. There's no path back to the battery. Well, we have 10 volts divided by 10 ohms, so that's 1 amp. Let's map those currents back to the circuit. We're going to have 0 amps flowing here. We have 1 amp flowing here. Put the A for amps on that one. And we have 1 amp flowing down this way. If we recombine the blue currents with the red currents are from the 2 amp circuit, the blue currents are from the 10 volt circuit. Superposition says that we can add all of those together and get the real currents. So 1 amp plus 0.8 amps, both flowing in the same direction, is a total of 1.8 amps. 1 amp flowing down and 1.2 amps flowing up means we have to take the difference of those two currents, and the higher current flows up, so we're going to get 1.2 minus 1 is 0.2 amps. And 1.8 plus 0.2 equals 2 amps. And 2 amps minus 0 also equals 2 amps. So these are all of the correct currents that flow in this circuit. If we clean this circuit up by getting rid of the mathematical currents and just leaving the real currents, we can now find the voltage drops across each one of these resistors. 2 amps flowing through 12 ohms is 24 volts. 0.2 amps flowing through 4 ohms is 0.8 volts. And 1.8 amps flowing through 6 ohms is 10.8 volts. Let's see if this makes any sense. According to Kirchhoff's voltage law, if we go around each one of these loops, all the voltages should add up. So if we start here at 0, and we go up around this direction, we're going to go up 10 volts. So this corner is going to be a positive 10 volts. We're going to drop 10.8 volts. So right here is a minus 0.8 volts. Then we go up 8 volts back to 0 volts. So that loop works. Well, here's your chance to try it. This is a circuit that's got one voltage source and one current source. Pay attention to the direction of the battery because it's upside down than what you're used to. So once you have the current and voltage for each of those 3 resistors, resume the video. Press pause now. Here's the result of the first circuit. 1.5 amps flow out, 0.9 flows up this way, 0.6 continues to go around here. The 0.6 and the 0.9 add up here to be 1.5 that flows through the 12 ohm resistor. And here is the result of our second circuit. We take out the current source with just the 15 volts. We've got 15 volts across a total of 10 ohms, which means that 1.5 amps flows through this 4 ohm resistor, 1.5 amps flows through this 6 ohm resistor, and it comes back to the battery. There's no current flowing in the 12 ohm resistor because of the open right here. We take those 3 values, map them back to the original circuit, and now we're ready to find the total current and the total voltages. .5 amps plus 0.9 amps is 2.4 amps. 1.5 amps flowing this way minus 0 amps flowing that way means that we really have 1.5 amps flowing from left to right. If 0.6 amps flows this way and 1.5 amps flows this way, the real current is going to flow in the direction of the larger current, but it will be the difference between these two. So this is going to be 1.5 minus 0.6, or 0.9 amps. Let's see if this makes sense with Kirchhoff's current law. We have 2.4 amps flowing into that node, 1.5 amps flows out this way, 0.9 amps flows out this way, and all the currents balance out. 2.4 minus 1.5 minus 0.9 equals 0. If we clear away our mathematical currents and leave just our real currents, we can now find the voltages. And there we have it. Using Kirchhoff's voltage law as a double check, we start at 0, we go up, we go down minus 15 volts, we go up 5.4 volts, so now we're at minus 9.6 volts, we go up 9.6 volts, and we're back at 0. Everything works out exactly like it should.